Good afternoon. Today I present to you Lecture 3, where we look at choosing impulse responses of the filter. Last lecture we looked at choosing parameters for filter. Last lecture. And today we look at choosing the impulse response of the filter. Now let's move on. Let's first define what an impulse response is. Impulse response. Well, an impulse response is when you send a spike, a signal, so that's amplitude in time, into your system, and then you measure what the wave or the graph comes out. It could look like anything depending on what's inside your system, but in simple terms, you send a spike into your system and then you measure what the output of the system is. Output of system. Now, that doesn't actually mean much because what's this got to do with filters? Well, the FIR filter is based on this principle of an impulse response. It's actually based on the impulse response of an ideal filter. So let's look at ideal filters. So if you remember last lecture, we looked at the frequency response of a low pass filter. So that is a low pass filter. That is the amplitude and that is a frequency. Well, this isn't actually an ideal low pass filter because it doesn't, you see, after the cutoff frequency, it doesn't instantaneously go to stop band. It rolls down a bit. Well, the ideal one, if you remember, looks like this, a rectangle. After the cutoff frequency, you get to 0. So here's 1 at low frequencies, 0 at high frequencies. High frequency. 1 at low. 1C. Now the low pass FIR filter is based on the impulse response of this ideal filter response. So let's look at that. Well, the impulse response is the inverse Fourier transform of the frequency response of the system. Now let's get a pen. Impulse response equals inverse Fourier transform of frequency response. Now mathematically that looks like this. The impulse response equals the integration from infinity to minus infinity should be of the frequency response multiplied by e to the power of j 2 pi fn. Yeah. Now I'll avoid getting too mathematical about everything, but trust me, this part's important. Well, our impulse response of an ideal low pass filter looks like this. Low pass filter is 1 before FC, which is cutoff frequency, and 0 after the cutoff frequency. So we are just putting this frequency response here into this inverse Fourier transform. Remember, the FIR filter is based on the impulse response of an ideal filter. So yeah, put that in there. And what that looks like is, so frequency response equals 1 when frequency is less than or equal to FC, or 0 when F is more than FC. Frequency is less than or equal to FC and it is 1, or when frequency is more than FC, it is equal to 0. And we are integrating this. Now, of course, you can't, if you integrate 0, you get 0, so there's no point integrating that. However, this part, we can put in there. So let's just do that. Rub this all out. So we have impulse response equals integration from, well, we said minus infinity to infinity. infinity to minus infinity, well, we're saying instead FC to minus FC. If you want our filter to be symmetric, that's why we're integrating from FC to minus FC. And the symmetric nature of the FIR filter allows it to have a linear phase. And well, that's why it has linear phase. There are some other advantages too, as I understand, but the main one you should know is we integrate from FC to minus FC because it gives us a linear phase. It makes it symmetrical. So now you just put 1 because, well, that's the frequency response of the ideal filter. From FC to minus FC is just 1 multiplied by e to the power of j 2 pi fn df. Now, I won't bother trying to solve any of this, but I'll give you the answer. And the answer is the impulse response is equal to sine 2 pi fn divided by pi n. And that's it. That's the impulse response of a low pass filter. Response. I should say an ideal low pass filter, that is. Now, this is also called the sinc function, or 2fc, 2 times cutoff frequency multiplied by sinc 2fcn. Now, most calculators don't know what sinc is. Like, your handheld calculator probably doesn't know what a sinc function is, so let's stick to this sine purpose here. Now, this part here is basically equal to sinc and plus some other stuff, of course, but that is basically what sinc is. This is the equivalent of sine divided by pi n. But of course, we will try to avoid using sinc because most calculators do not accept the function sinc, but they do accept sine. So let's just keep going. So we said the impulse response of ideal low pass filter is sine 2 pi fn divided by pi n. Now you have this, oh, that's fc, that is. You have this variable fc, and that is your cutoff frequency. However, this cutoff frequency is not the real actual cutoff frequency you say. So if you wanted your cutoff frequency to be 400 hertz, you don't stick 400 hertz into that fc. Instead, you use a normalized cutoff frequency. Now, this is our normalized cutoff. But what does that mean? Imagine if you wanted in real life, you wanted to remove 400 hertz. So cutoff point FC is 400 hertz. In real life, if you want to remove 400 hertz, well, in the FIR filter, we're using a normalized cutoff frequency, not the actual real life cutoff frequency. So how do you get from 400 hertz to the normalized cutoff? Well, normalized cutoff frequency is equal to FC equals FC real, we'll call that, the real one, divided by Fs divided by 2. Now let's decode that. What is Fs? Well, Fs is the sampling frequency. Why is it Fs divided by 2? Well, there's something called Nyquist's law, or Nyquist frequency. Nyquist frequency. And Nyquist frequency basically means that Fs, your sampling frequency equals 2 times the max frequency present in your signal. So if the highest frequency found in your signal is, say, 800 hertz, then Fs would equal 2 times 800 hertz. So Fs equals 1600 hertz. So you choose now typically you would choose your sampling frequency way higher than 2 times the max because it gives you a clearer signal, the computer has a clearer understanding of what the signal shape is and the signal is. However, the minimum sampling frequency you need is 2 times the max frequency present in your signal. Okay, now we said we wanted a cutoff point of Fc equals 400 hertz. So we would put our 400 hertz here, and we would put Fs over there. So make some more space. Go back to purple. So that's 6. And so that would equal normalized cutoff equal 400 divided by 1600 divided by 2. That is the same as a half. That is your normalized frequency. Normalized cutoff. See. And so you would put 0.5 in here if you have a sampling frequency of 1600. And that's the point. If the sampling frequency changes, FC is not 0.5 to filter out 400 anymore. It will be different based on this ratio here. If you need FS to be, or the sampling frequency to be 2 times the max frequency present in our signal. So let's take this sine wave here. You have one sine wave cycle. That's in time and amplitude. For your computer to recognize this is a sine wave of a certain frequency, it has to be able to sample it twice. So that could be one here, one here. It could alternatively be here or here. All the points is it has to be able to sample it twice per sine wave's frequency. So if this is a 2 hertz signal, for your computer to recognize it's a 2 hertz signal, your sampling frequency has to be at least 4 hertz. Remember, Fs equals sampling frequency equals 2 times your max frequency. If your max frequency is 2 hertz, you need 4 hertz at least. I will say at least 4 hertz because this is the bare minimum. Having 2 samples per cycle is the bare minimum. In reality, we tend to use maybe 10 times, 5 times, maybe up to 20 times the max frequency. So if you have a 2 hertz maximum, if your max frequency has 2 hertz, well, you would typically use, say, a sampling frequency of 20 hertz or 40 hertz or something like that. That allows us to recognize more things about the signal. Is more advantages to using 10 times than just using 2 times. Now, 2 times is good if you have say a little microcontroller and it's very low power and you want it to be as efficient as possible. Then 2 is all right, but if you're making an oscilloscope or something, well, then you want to have something higher, like 10 times. So what is this value here, n? Well, you see, in a continuous wave, the way we would see it at least, signal, the way we see it as in, sorry, that's time. Sine wave would look like that. Well, you see, a computer cannot see continuous time. It can only see discrete time. So let's see that. And it sees it as samples instead of time. So n is samples. So to a computer, a sine wave actually looks like this. Etc. You see, it sort of makes a sine wave look, but it's more of a staircase, isn't it? But that is how a computer would see. And each of these would be samples. So that'd be n equals 0, sample 1, sample 2, sample 3, sample 4, sample 5, etc. It doesn't look at it as in t equals 0 to t equals infinity. Samples are discrete points. You see, there's at sample equal 1 and 2, the amplitude is basically the same throughout that entire time. Well, that is what it's a discrete system. You can't have a change of amplitude in the middle of that. A computer will not recognize that. And how often you're making these samples is known as the sampling frequency. So the more staircases, so if you have steps like this, that would be a lower sampling frequency. Sampling frequency. And if you have more of these steps, that would be a higher sampling frequency. And that is, in essence, all n is. N is just the samples of it. The higher your sampling frequency, the more often n occurs. Now, the FIR filter, FIR low pass filter, is based on the ideal low pass impulse response. So we came up with the ideal low pass impulse response as sine 2 pi fn pi n, also known as sync 2fc sine 2fc sync. That should be it. Now I'll avoid using that again because it's no calculator accepts it. Well, this wave, if you draw that in a graph, that looks like this. Let's go for more time. And that is in essence what a sync wave looks like. Now this goes on forever, so that is 2 to infinity to minus infinity. That is infinity. Amplitude. Now this is what the ideal low pass impulse response looks like, and it goes on forever. So that will continue, or it'll keep getting closer to zero, but it goes on forever. But remember, via FIR filters, we are finite in nature. We're not going to let this go on forever because that will be too computationally expensive. So we restrict it. and we restrict it with something called a window function. Now to restrict it, we are basically making this finite in nature, so we are only accepting the impulse response up to here. So by applying a window function, all you see is this. You don't see any of that. And this is what gives FIR filters its finite nature. Now, window functions is explained later in the course, but this is essentially how the FIR filter is made. It takes the ideal low-pass impulse response, which is this goes on for infinity to minus infinity, this impulse response sync wave, and it just applies a window function to constrict it. It's constricted in time. And remember, that axis is time. This goes in time. Impulse response is in time. Now, just another quick note on this. You can see that this sync wave is symmetrical. Whatever happens after this line, it's the same signal. It's symmetrical. Symmetric. Now, I previously did say that the reason we have a symmetrical signal is because it gives it linear phase. This symmetrical quality gives it linear phase. And just in case you're wondering, this is minus time and time. Now, don't worry about trying to understand that. Just understand that it's symmetrical, and symmetry allows it to have a linear phase. So yeah, don't worry if you don't understand too much about how you get to this place by the inverse Fourier or anything like that. Just know that the FIR low pass filter is equivalent to that. So that should be a FSC here. That's all you should worry about. FIR low pass filter is based on this equation here. Don't worry about too much about getting there. The mathematicians have done that for us. If you just worry about this is the value you get. Now, a high pass filter, a band pass filter, a band stop filter will have a different equation, but very similar to this, similar in nature. It may have this sync-like nature, and that's what we'll discuss in the next video. Thank you. Please like and subscribe. See you next time.